Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 3.1.3, which is using a probability model. And so the initial parts of this 3-23 problem involve you and your teammates playing rock, paper, scissors. But because there's only one of me, I don't think I'll play it against myself. Just take a second, pause the video, read the rules about how each player earns points. Player A will get a point each time all three players match. Player B gets a point when 2 out of the 3 players match, and player C gets a point when none of the players match. And we're supposed to devise up a tree model that demonstrates the probability of player A, B, and C getting points. So we're only going to do parts D and E because that's the part that requires the actual instruction of the material. So let's go and make a tree diagram. Now I'm actually going to make a tree diagram a little differently this time. Usually my tree diagrams go sideways, but because of the amount of possibilities that could happen, it actually makes more sense to do the tree diagram vertically. So I'm going to start with the rock, the paper, and the scissors here. And then from here, each one of these, right? Each one of these is going to produce another scenario where this R is the first player. The second player has the ability to produce a rock, a paper, or a scissors. And then from there, the third player has the opportunity to do the exact same thing where they're going to do a rock, a paper, a scissors. And then this guy here, and I don't have enough space, I should have timed that out better, a rock, a paper, a scissors. And then this guy, again, not enough space. I'll learn that for the next diagram here, a rock, a paper, a scissors. So I'm going to go ahead and pause the video real quick and complete the rest of the diagram. And then I'm also going to list out all the possibilities like rock, 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 paper, scissors. So I'll pause the video, come back and do that. If you want to, feel free to pause the video and join me in a second. I'll be right back. Okay, so after mapping all of them out with rock, paper, scissors, and the way we did it, I ended up calculating all of the different ways that the possibilities could happen. And there are 27 total outcomes, right? 3 down, 9 total columns. And so from here, let's calculate the probability of player A winning. Remember, player A will earn a point if all 3 players match. So let's take a look at what that looks like here. So rock, 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 paper, 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 scissors, scissors, scissors. So that's 3 out of the 27 total outcomes. So he'll get 3 out of the 27. I'll reduce that in a little bit, but just to keep all the probabilities the same, we'll not reduce for a little bit here. The probability of player B earning a point, so I'll go ahead and highlight those in a different color here. And that there's a lot of them, right, where 2 players match. So let's go ahead and go with this here. 2 players matching here, 2 players matching here. Let's see, I don't see any match. Let's say one guy here, one guy here. I feel like it's about 2 per, so that would be PRR, PRP here. This guy and this guy. Let's see, this guy and this guy. I figure it's about 2 per column. So, if we can just kind of look for that, then I think we'll be good. Here and here, and then here and here. Okay, so cool. So we got 1, 2, 3, 4, 5, 6, 7, 8, or 2, 4, 6, 8, 10, 12, 14, 16, 18. So 18 out of those 27. So player B looks like they have a really easy time here. And then from here, the probability of people not matching at all is just going to be like these guys. Oops, wrong color there. I want to do that in red. Here, 1, 2, 3, 4, 5, 6. So 6 out of the 27 possibilities happen when none of the players match. And I'll go and write down that probability explicitly here. The probability of player C earning a point. So if we reduce these, that would be 1 out of the 9. That would be 2 out of the 3, and that would be, looks like they both divide into 3, so 2 out of the 9. So clearly, player B has the greatest advantage in this game. The next question deals with whether or not the game is fair. Clearly, it is not. So we can just write that down. The game is not fair because player B has the highest probability of earning points. So in order to make the game fair, what you have to do is you have to assign a point system. So they actually came up with a way to make the points actually viable. Honestly, just make the guy with the least probability. So a way to make the game fair is to make player A's points worth more, and player C rather, and player C's points worth slightly more. So almost like a handicap in Super Smash Brothers or Mario Kart, where like you get better items if you're coming in from behind. Okay, so that is a probability model of rock, paper, scissors. Let's move on to the next problem. I'll be back in a flash. And we're back with problem 3-24. It says there is a new game at the school called Pick a Tile, in which the player reaches into 2 bags and chooses 1 square tile and 1 circular tile. The bag with squares contains 3 yellow, 1 blue, and 2 red. The bag with circles contains 1 yellow and 2 red. In order to win the game, a player must choose a blue square and a red circle. There's that "and" word again. You should be thinking about a certain mathematical operation. So we got to explore the game using the E tool, but the game costs $2 to play, and we have to decide whether or not we're going to play this game. So Jerry suggests to list all the combinations and the circles. Jerry says the answer is 1/6. Do you agree with Jerry's answer? Probably not, right? Because the probability of choosing this assumes all of the probabilities are equal, like equally likely, but clearly the probability of choosing a yellow square is higher than that of choosing a blue one. So I don't think Jerry has the right idea here. So this assumes that the probabilities are equal. They are not. So A, goodbye. It says make a tree diagram for this situation. Okay, let's go ahead and do it. And so let's go ahead and start off with our first scenario here. We've got red. We've got yellow, and we've got blue. And so let's go ahead and start off with our tree diagram here. So in our first pull, we've got 3 scenarios. We've got a red square. We've got a yellow square, and I'll scroll down here, and we've got a blue square. Now, each of them has a different probability of being pulled. So from here, let's try it again. So there's 3 plus 1 plus 2. That's a total of 6 total squares. So out of yellow, you have a 3/6 chance. I know that's 1/2. I'll take care of that later. Let's see, 2/6 of a red and 1/6 of a blue. Now from this red, notice how it doesn't say that whether or not you pick from the square affects you picking the circle. Now we've got 1 yellow and 2 reds. So again, that's 3 total circles. So 1/3 yellow, 2/3 red circle. And then we'll do it again. 1/3 for yellow, 2/3 for red, and we'll scroll down here to the blue. 1/3 for yellow, 2/3 for red. Okay, so now remember to take into account the duplicate tiles in the bags. Okay, we got that already. We're good. What is the probability of choosing the winning combination, a blue and then red, blue square, then red circle? So we want the probability of the blue and the probability of the red. So the probability of the blue is 1/6, and the probability of the red is 2/3. If I multiply those guys together, because this is the and clause, what we're going to get is we're going to get 2 over 18, or 1/9. The 1/9 probability of getting it. And so they're saying, should Jerry and Marty play this game? Would you? Why or why not? I wouldn't play this game. You have a 1/9 chance of winning? There's no way I would not play this game. I'll just say it. I'll type it in. I would not play this game. Because, first of all, it costs money. It costs money. And the probability of winning is very, very, very low. So no thank you. I will spend my $2 playing Simpsons Arcade. Okay, let's move on to the next problem, and I'll be back in a flash. Problem 3-25 wants us to use an area model to represent this game, the pick a tile game, rather than a tree model, and then decide which one you think is better. This is actually a very subjective question. Ultimately, it's going to depend on you what you want to use as your area model, as your probability model. But let's go ahead and try it out real quick. So I'll go and call this bag 1, and then bag 2, and let's go and draw this area model deal out. Oops, I'll move this guy over a little bit. Oh man, I don't think I have enough space here. Okay, so from here, bag 2, I believe, had just the yellow circle and the red circle. Bag 1 had the red, yellow, and blue. I gotta move that bag 1 out of the way here. That was dumb. Okay, cool. So now from here, this I believe had a blue, a yellow, and a red. So what I'm going to do is I'm going to put the individual probabilities next to them. I got to refer back to the chart here for a little bit here. So red was 1/3, yellow was 1/2, and blue was 1/6. I'm reducing the fractions just because it'll help me when it comes to multiplying. So from here, this is a 1/18th chance, a blue and a yellow. Let's see here. A yellow would be 1/6. Red yellow will be 1/9. Blue red will be 2/18 or 1/9, which is exactly the probability we saw here. Let's see. This is going to be 1/3, and then this is going to be 2/9. Whoops, 2/9. So we have to explain why this is called an area model. So it's called an area model because each square's area represents the probability of the two events happening. So this is called an area model because each square's area represents the probability of both events happening. So, for example, a blue, then a yellow, or a red, then a yellow. Okay? And so discuss which model you would prefer. Honestly, that's a subjective answer. It's entirely up to you. We're not going to restrict you guys on which one to do. And then could you have used the area model for the rock, paper, scissors problem? Why or why not? Now, that's actually a really important question. We can't. And we cannot use this model for rock, paper, scissors because there are 3 events happening in that example. And the area model is good for two-way probability, right? 2 things happening, 2 bags, and that's it. Even though there's 3 things in one bag, there's one bag and there's one bag. In the rock, paper, scissors model, there are 3 players at play. So you would need 3 dimensions in order to represent this thing using some type of area or volumetric model. In other words, you would probably need to do a volume model in order to do 3 players or 3 events happening. We don't have that ability because we can't draw in 3D. But that's okay. The area model is good for two-way probability, so 2 events happening. All right, I'll be back with the next problem. All right, let's take a look at 3-26. We got Mr. McGee here, has a 70% free throw average, and the opposing team is ahead by 1 point. He's got he's at the foul line, he's about to do a shot, and blah, blah, blah. A lot of exposition with these probability problems here. First, it says take a guess. I will leave that to you. Let's go ahead and draw a tree diagram to represent this situation here. Basically, the underlying issue here is that if he makes the first shot, he can go for the second, but if he misses the first shot, he's done. And so let's calculate the probability of each one. So from here, let's do a tree diagram. So the first one is going to be if he makes it. So I'll just call that yes, okay? Because makes and misses is actually the same letter, so the next one is going to be no. So this is 0.3 and 0.7. Now if he misses or no, it's over. It's all good, or in his case, it's all bad. Then the next one is going to be another one. So another yes and another no. So another 0.7 and 0.3 right here. All right, so here's our tree diagram. It says Jeremy is working on the problem with Jenna, and he remembers that area models are sometimes useful when related to this kind of probability. They set up the probability models and discuss them with your team. What part of the model represents rim shot getting 1 point? How can you use the model to calculate the probability? Blah, blah, blah. Okay, cool. So let's go ahead and calculate some probability here. So let's go ahead and find out the total probability that he makes both shots. And so that's going to be 0.49, 0.21, and then misses is just going to be 0.3, because if he just misses it, then it's all over. All right. And so let's go ahead and calculate the probability that rim shot will get exactly 1 point. And that is dictated by a yes and a no, so that would be a makes and misses intersection here. So the probability of 1 point is going to be 0.21. Now you could have gotten that from the area model, which was the intersection of the 2 lines, or you could have multiplied the probability of yes and then no, giving you 0.7 times 0.3, 0.21 or 21% chance that he's going to get only 1 point. And it says using either your tree or area model, calculate the probabilities that he'll get either 1 or 0 points. And so the probability of, the probability of 0 points is going to be 0.3 or 30%, and the probability of getting 2 points is going to be 0.49 or 49%. The most likely is that he's going to earn both points. So again, intersection here for the 2 points, or you could have done 0.7 times 0.7. Okay, let's go and take a look at the next problem here. I'll be right back. And in 3-27, they're asking you to reevaluate your area model from 326. So I'll go and pull it up on the board here. It says, what are the dimensions of the large rectangle, and explain why they make sense? Well, the dimensions from here are going to be, looks like if we added those guys together, it's 1. And if we added these guys together, it's also 1. So it should be 1 by 1. And it should make sense because when we're looking at this thing in total, the entire area of all of this is 1 square unit, 1 unit squared. And so that would represent 100% of probability. In other words, the probability that any one of these events would happen. And that's what's going to happen if we add up all of the areas of this thing. And so from here, what is the total area of the model? Well, the total area of the model is 1 unit squared. I just wrote that down right here. And express the area as a product of the dimensions and as a sum of the parts. So I could say 0.49 plus 0.21 plus 0.30 or 0.3 would be equal to 1 times 1. So that's the area as a sum, and this is the area as a product. So area as product, area as prod, area as sum. So there we are, back again, right? Those area models are making their triumphant return. And what events and probabilities are represented by the entire area model? Well, in this particular scenario, the events and the probabilities are, I'll go and type these in, the events and probabilities, the events are the probability of rim shot making either 0, 1, or 2 points on his free throw, right? And so what they're saying is, what does the area model represent in the context of the problem? Well, it represents probability of making certain types of shots. So to summarize this chapter, or this section is basically showing you how to pick a model that works best for you. And so, as always, when it comes to area model, it's for two-way probability. You can use the tree model on two-way probability if you want to. The area model works just as fine. But anything more than 3 events happening, then you're going to have to use a tree model for that one. That, for example, the rock, paper, scissors being our primary example. So anyway, that should do it for this video. As always, leave comments or questions in the comments area, and I'll see you in the next one.